could return to this notion of composition of inverse functions. When we first talked about the fact that inverse functions undo each other, we talked about the fact that that means that if you compose them, if you do one function and then you do its inverse, you're going to be right back where you started. Okay. So it will always be the case that f of f inverse of x is just x, and f inverse of f of x is just x. Here I start with x, I do something, I undo it, I'm right back to where I started. Same thing here. Whatever f inverse does, f undoes it. They're opposite processes. So that takes me right back to x. Okay. In fact, we can use this as a test to see whether two functions are inverses. So, if two functions f of x and g of x are inverses, if and only if f of g of x equals x and g of f of x is equal to x. You do need to check both of them. Both need to be true. Okay. So we can use this to actually test to see whether two functions are inverses or not. Now, if you're just asked, are these functions inverses, one way that you could check would be to take one function, find its inverse. If what you get is the other function, then the answer is yes. But if you're asked, use composition to see whether these functions are inverses, then you're being asked to do it this way, to look at both compositions, to see if the following are inverses. So let's let f of x equal x cubed minus 1 and g of x equal the cube root of x plus 1. So I am seeing some opposite processes going on here. Here I'm subtracting one, here I'm adding, there I'm cubing, there I'm taking the cube root. So this seems reasonable that they might be. Let's check. So, doesn't matter which one I check first because I'm going to check both of them. F of g of x simply means that I'm taking f and what I'm plugging in is the cube root of x plus 1. Now, in the formula for f, x was just a placeholder for my input. So where that is, I'm going to plug in the cube root of x plus 1. We're going to cube it, and then we'll subtract 1. Okay. So what's inside the parentheses here goes inside the parentheses here. So I get the cube root of x plus 1 cubed. Well, that's just going to be x plus 1, and then we subtract 1, and we get x. Okay. So f of g of x does simplify to just give us x. That by itself is not enough for me to show that these are inverses. I have to check what happens if I compose them in the opposite order. So let's now look at g of f of x. By the way, if I had, in evaluating f of g of x, if I didn't get x, one of them not working is enough for me to say, no, they're not inverses. But one of them working is not enough for me to say that they are inverses. Okay, so g of f of x would be g of x cubed minus 1. So with the g function, there's where I'm putting my input. So we're looking at the cube root of my input plus 1. What's going in here is x cubed minus 1. Now it turns out those parentheses aren't really necessary. What's under the radical is just x cubed minus 1 plus 1. I can simplify that to just x cubed. And the cube root of x cubed is just x. So the answer is yes. These are, in fact, inverses of each other. Okay. Now, what that means is if I wanted to, I could say g of x is actually the same as f inverse of x. I could use that name for it. Or I could say f of x is g inverse of x. So I've got alternative names that I can use once I've determined that they're inverses of each other. I didn't know that ahead of time. All right, let's just try another example. Let's look at f of x equals the square root of x, and g of x equals x squared. Now, I pretty much know that the answer here is no. They aren't inverses of each other because we've established time and time again that x squared is not invertible. But I want to look at this example because I want to show you why it's necessary to check both compositions. Okay. If I take a look at g of f of x, that would be g of the square root of x. Now, what does g have me do? G has me take my input and square it. So I'd take the square root of x and I would square it. Okay? That would give me x. Okay? If I square a square root, I get what's underneath the radical. Okay, it looks like it worked. But if I check the other composition, f of g of x, that would be f of x squared. F is telling me to take the square root of my input. So I'd be taking the square root of x squared. That would not give me x. That would give me the absolute value of x. Okay. So this one looked like it worked. This one didn't. Okay. Now what's happening here is the reason this one worked is that by taking the square root of x first, we put some restrictions on x. X had to, in order for this to be defined, be non-negative. So if I have a non-negative number, then I can take its square root and then I can square it. But we didn't have that restriction that x had to be non-negative here because the first thing that we were doing was squaring it. Okay. So it is necessary to check both compositions, and we will return to this example in a little bit when we're talking about the domains and the ranges of our inverse functions.